It's not impossible, it's just very hard. Why this bothers me is it's like you're in a dream and somebody's like, oh, we've got the solution right here, and you try to look over their shoulder and you can't quite see it. You know that there's something there. I can't put my hands on what the right answer is, though. It feels like this is a solved problem by somebody who's not us. Anyway, welcome to Wednesday, guys. So today I want to go over the last little conversation we had from assignment 1. Coming up, I will post this weekend at the latest assignment 2, which is going to be a couple of more Excel files practicing fitting like we've sort of gone through before. So this is the multi-step palladium cascade we've been talking about. I'll give you experimental data to sort of mess around with that, to sort of play through. And then there's a couple other challenges based on what we'll be discussing coming in next. Reminder also, please start thinking about your papers. I don't know when we set the hard deadline, but basically by the end of June or January, we want to make sure that everybody selected a paper and it's locked in. I do have one person that mentioned that there's a time conflict with the presentation schedule, so I will attempt to shuffle it. Asterisks. This may kick off a whole domino series where that person moves and now there's something else. I'll try to get this locked in. But did everybody check your schedules based on where you've been assigned? Is there anything else? Has anybody come up with, I have a midterm, I have a completing class, anything else like that yet? No? Okay. Again, we'll get that put out. But what it looks like, again, because of the class size and the components, what you're seeing is most of March will be class presentations, right? So it means that the content stuff we will focus on is going to basically be through the rest of January and February, and I'm adjusting accordingly from that point. Yeah, where we left off, we talked through this question, what's the order in the system? The quick answer is it's complicated because of this competing activation and rate limiting step. The answer you get to what is the order is really dependent on the range that you're sort of interrogating. There's no one single value. It's contextualized based on the absolute K values you happen to choose, but also the relative concentration ranges that you're dealing with. The last one I wanted to talk through is what happens specifically if you start playing around with this value here. So I was saying go through and I want you to make a rate of product formation on the y-axis. X-axis is going to be your concentration of Y, so, of A, excuse me. So in Capacity, you built a plot that should look like this. Remember, the way that this one reads, if you think of it temporally, this is where you start at this concentration. So time equals 0 is this high concentration of your substrate A. And as the reaction runs, you're moving from right to left. It's not the normal left to right sort of time course. So it takes a little bit of a jump that this is visually how you would interpret this. The experiment actually starts at 0.1 molar in A and then is consuming A as you run through. And what you're reading is how fast the reaction runs. The one part I wanted to flag was because, and this is a scanning exercise, I'm saying I want to check what happens as I vary the activation step from very slow, in fact, even slower than what we set the rate determining step over here, to reasonably fast, right, as we walk through. And if you notice, I'm doing jumps of orders of magnitude. That's a logarithmic scale, right? So this is log base 10 is what we're trying to do. So instead of plotting this, where I said I want 3 intervals, like you could go through and manually set the K value to that this activation, run the plot, look at the plot, interrogate it. The faster one to do is say, look, I want 3 intervals, so 4 different experiments, and I want to vary from that very low to that very high, and I'm going to do it on a logarithmic scale. That will just automatically pick that series, right? So it will show you from here to here to here where you're doing that sort of base 10 jumping. So this is what that rate versus time plot looks like. In your own words, what's this saying? Like what is happening here if you imagine temporally from the high concentration A on the right to low concentration on the left? If you had to describe this, what do you see? How is rate changing with A? You can break it down first for an individual experiment compared to as you move through the experiments.
I mean, for the top one, you have, assuming that's the one that has a really high
activation, yep.
Yep. You're actually going to start off going really fast.
Yep.
You're really going to consume A, get up to a high rate, and that's just going to fade off.
But look at the fade. Right? So you're right. Here, if we go to this point where the activation, so I've basically made this fast enough that pretty much I'm throwing the precatalyst in, I'm going to populate my system. it's going to hit steady state pretty quickly. I don't have this huge population of pre-catalysts slowly going into the system. That's as normal as you're going to get, right? So that's true. That means that you start the chemistry and it lights off. It comes up to your maximum rate pretty quickly, very early both in time and very early in concentration of A, right? So it starts up here. Good. As I consume A for some period of time, is my rate changing? A little bit, right? It's not, like remember, if this was a normal first order plot, if you tried to look at this same plot for a first order system where we took rate is equal to K times concentration of A. Let's say that. That is the equation of a straight line, right? If I were to graph, in that case, again, rate of product and concentration A here, I would expect that, where the slope is K and I have a descending plot. That's it. That's not what this is. This looks like a zero order process, right? Because the rate is consistent for some chunk of time, almost, right? It doesn't vary a lot in this time. Towards you get to the end of the concentration over here, that's where it starts to come off. But in each case, each of these lines kind of looks like, at least when it hits maximum, it's holding that rate for some period of time. I'm holding that rate for some period of time. I'm holding this rate. I'm holding this rate. You've got a straight across line. Now again, in a perfect world, if we were here, truly zero order processes look like that. Right? Rate is constant with time because the equation just looks like rate equals K. That's not real because it takes time and energy to reach steady state, and it takes time and energy to fall from steady state. So you have both initial or initiation kinetics, which is represented, and you have terminal kinetics. The end of the reaction, you start to lose the last parts of it. So I'm just trying to emphasize the difference between true ideality and then what a system will actually do. This is kind of that point. All I'm trying to come down to, though, is that they all have some sort of zero order behavior. As you increase the activation behavior, it goes from more parabolic, like we showed last time, to more square wave, right? That parabolic one that I showed you with Donna Blackman's one, that perfect sort of like, symmetric parabola, that's indicative of a case where the activation step and the turnover limiting step are about the same. If they're balanced, you end up with something that looks nicely like a perfect, x squared kind of function, right? The more you get to super fast activation and super fast death, the more it gets to this square wave, and everything in between is going to be some convolution where you've got gradients at these two edges of the system where you're getting more rounded, basically. So those are your two extremes cases. If you go to the plot, so these are still the rate plots, this is the plot of concentration of A versus concentration product. So as A gets used up and product comes in, that super slow one here, that's that sort of barely taking off. You look at the product formation in the second one versus the third versus the fourth. Remember, as I move through these, this is that highest, activation is stupid slow. This is actually the activation we were using for the system where it's balanced with the turnover limiting step. This will look most sigmoidal. This one, activation is getting faster. Here, there's almost no activation available. You see that when you start the chemistry, you no longer have this induction period at the beginning. It's almost gone. And that's really what we're ramping up. If you go and look at the slopes, though, what's interesting about this one, remember, this is now your concentration versus time profile. What I was trying to emphasize is it looks like it is zero order. The rate is not changing with concentration A. That's kind of what you're showing here. The concentration of product coming in is the rate of that, remember, is the d product dt, and it's a straight line through this part here. You have it's basically pinning the system. It's making product as fast as it can, so concentration of product is rising according to a straight line. You can also go back and look at the speciation. This is what we went through, and once again, just you focus specifically on what's happening with this intermediate here. This is that darkest line right here. Initially, if your activation is very slow, you've just got this convolution. As you add, if this gets faster and faster, it starts approaching that true case where everything is piling up right here. This is the main dominant species. Only this step becomes your turnover limiting step, and it becomes sort of what we've say the prototypical reaction, which is only being turned over based on that reductive elimination. It just means that instead of having a distribution of species between all four of these different components, they're now piling up over here. So again, I've posted this version of the Copacity file online. Use it. It's a good template to use under these different extremes and sort of practice your assumptions about how the system would look. I believe all the plotting data is already in place, so you can just use it to sort of show, you don't have to create new plots to visualize these things. So the last part, as we sort of mentioned through last time, is what's happening here when we start talking about order. Order is being convoluted depending on which part of the curve we're dealing with. This is what we mentioned about the Michaelis-Menten equation. Under some system where concentration of S is very, very large, it behaves just according to Vmax. Under concentration very small, we get this other. And then in between, you've got sort of a variation. This is where we mentioned last time that if we tried to plot the rate versus concentration of S, we're getting this kind of an increasing behavior where it's truly zero order over here, truly first order over here. So this is just, again, up until now, we were mentioning that this is a phenomenon. What we can now start doing, though, is use it as a feature for interrogating mechanisms. So this is a paper by Jordi Burris. It's in a relatively obscure journal called Topics of Catalysis. But it's worth grabbing this and taking a look at it if you want to learn more about sort of some of this idea. What he was doing in here was just to call question of, like, a lot of people apply order like it's a melting point in a system. Having an order equal to 1 meant a very specific thing about a mechanism, and the answer really is that's not true with catalytic systems. You're going to get a particular order behavior relative to what Ks you have, what concentrations you have. It's specific to a lot of other features. So don't use it as a holy number that, well, my reaction was first order, therefore everything else must fall into place. The answer is maybe. Really, all he was showing was that he was reminding people that Michaelis-Menten curve exists. So as we increase the concentration of A for this toy system, where once again you notice that we've got similar K values for both the retro reaction and the forward reaction. This is a case where you have a really high sort of curvature that's associated here. He does go through a little bit of the math behind it, but the point I just want to focus on is that you can kind of generate these two kind of plots. Up at the top is the one we've been doing where it's the rate of the reaction, and you could call that the instantaneous rate of the reaction against the concentration or initial concentration of A. If you were to think about this same process over time, it's kind of like what we've been showing with this graph here. How you would read this graph is, I start the reaction right here at a high concentration of A. The rate at that initial time, imagine if it just starts perfectly, will be very high. And as the reaction runs, we're consuming A, the rate starts to drop. So there's a period of time where it's mostly zero order in A, and then it starts to fall into a range where it's mostly first order in A. This is what we've been doing. That's the Michaelis-Menten plot of how the rate is varying according to the overall reaction progress. This is what the order at every one of those time points would look like. So it starts over here at a zero order kind of process, and then it sort of comes towards it approaches a first order process. This generality, and then this is really just, it's a form of advanced calculus is what this comes down to. There's a constant in calculus that you can use for these kind of perturbational systems called the elasticity constant. So what it's not think of it as just a first derivative or second derivative. And again, I'm only just mentioning this in case you guys want to dig into the math of it all. But there is an actual fundamental math in calculus that talks about variations in variational systems. So it's this weird double meta thing, right? And it practically, for what we care about, these kind of direct plots, rate of a system as the reaction runs in terms of concentration is probably the most meaningful for us. Well-behaved normal systems will be nice straight lines because the rate is constant for the entire concentration of the system. Any catalytic system is going to be some variational one where you have partial saturation kinetics and not. That's just the qualitative assessment that you guys should be comfortable with. When we start to apply this, though, how this becomes useful is if we have trying to quantify what happens in the terminal kinetics phase. So what happens as either the reaction gets started, so understanding what that activation behavior is can tell us about, maybe a different ligand or a different condition can help more of the catalyst go from a pre-catalyst on cycle. So understanding what that light-off behavior is. The second is how the reaction runs down. There can be a couple of really important fingerprints that tell you about what kind of a mechanism you have. In the example I gave you for your assignment, we purposefully set initially these concentrations, and we set the activation and the rate limiting step equal to get that kind of parabolic, this kind of parabolic rate versus concentration curve. It was set up that way to have a nice, clean sigmoidal curve. What I want to show you is another really important feature that you can sort of drag out. So in that same system, I'm going to keep the initial concentrations just like I did. So ligand is 0.02, pre-catalyst is 0.01. I have an excess of my A, my first reagent, and I have a limiting reagent is my B1. So this goes to something that we talked a couple times, some questions in class was the same. If I'm going to do an experiment, I'm planning this experiment, and I want to vary the concentration of A to determine its order. Well, how big of a jump do I want to do is one problem you run into. So if I normally would have run this reaction, concentration of A is 0.15, is it appropriate to do 0.14 or 0.13? How big of a variation do you need is one question. The second, too, is what happens to systems as you start to change or invert your limiting species? So remember when we discussed this, we were using this as an example where this first step is under saturation kinetics, so it's reversible. And we said this is our turnover limiting step. I'm using this as my limiting reagent. I want this to be in excess because I'm trying to drive that equilibrium towards this species. That was done by design to say I'm trying to knock out that first step completely. Okay, but what might happen if I actually invert the two? So right now, if I take these parameters, and I've got my little Kopassi, what I did is two changes, just to make it a bit simpler. I'm going to increase the rate of my activation, so it's now big, it's no longer slow. I'm going to really jam that fast, so the forward equilibrium constant for that first equilibrium is now much larger. It's 1,000, where I'm actually cranking up the forward rate constant, and I'm keeping the reductive elimination to be relatively slow. That last product elimination step is wicked fast. So I've specifically locked it down where what I'm trying to do is say, transmetallation is my slow step here. This is stupid fast, this is fast, and this is really, really forward. I'm really perturbing the system to become as ideal as I can within reason. So I've set it up so that I'm expecting this to be my turnover limiting step. Now, first principles. If you know in advance, if you look at this system, I told you catalyst activation is fast. Reductive elimination is fast. Oxidative addition is very forward and fast. Transmetallation is slow. What do you expect the orders in ligand to be from that sort of a setup? Everybody in one creepy voice says 0. Perfect, right? It's fast. As long as the concentration isn't widely out of sight point, it's going to be quick. I don't care. Order in A, the oxidation step, the aryl halide. First, 0, negative, probably 0, right? Because it's quick. Order in transmetallation, order in B is, because it's in the rate determining step, should be first, right? Reductive elimination is fast and irreversible, shouldn't have any product inhibition. That's really all I'm saying there. That adding product to the system isn't going to care. It's just, blah, it happens. But I'm not going to see any buildup of, I won't see any buildup of this intermediate, I won't see any buildup of this intermediate, all of this should come on cycle. It should be as simple as I get where everything locks up here, this is my turnover step, first order, 0 order, 0 order, 0 order is what I would expect is sort of a numerical when it's steady state. That lines up. Okay, so if I run this now, and I just run a single time course, bloop, let's get rid of that. First thing I want you to show you, oops, sorry, I'm jumping ahead. Let me set this to 0.15, and we're going to run the time course. Boom. Under these conditions, this is my time course plot. Ah, crap. I need to bring a mouse to class. All right, don't want to look at that one. Don't want to look at that one. This is what we want. Time course plot looks like that. It looks like a normal first order process, right? Nice shape, products going on. That's great. If you look at the other components in this system, so run it again. This is my rate of product formation where concentration of A again is on the x-axis. That's this one we talked about before, rate versus concentration. If you notice, it's now a diagonal line like we said, right? This is a normal first order process where the K is that slope right here. Reaction comes on, goes as fast as it can, runs down. I've plotted here, the difference between blue and red is just I'm plotting the rate as a function of A and the rate as a function of B. Now remember, since both of them consume, this is not about order in A and B. All we're saying is that the reaction has to run in both. It is a first order process. That's really all this is telling us. I can't tell individual orders from this one experiment because both of them are being consumed as we run through this. But that's what the sort of prototypical would look like. If I now go through and only thing I do is I'm going to decrease the initial concentration of this to start becoming slightly limiting. So instead of having B as my limiting reagent, I'm going to use A as my limiting reagent. What should this do? So what do you think the outcome is going to be when I do that?
Should be linear initially, but we should start seeing some curvature later on due to it being limiting.
Right. If you think of it here, at our ideal system was this, right? We have a fast on, reaction initiates wicked fast, it runs to completion, that's all good. If I've now meant that I am missing A, but I still have extra B, this is probably going to initiate fine. The initial kinetics will tell me it's zero order in A. This change should not change anything, so the maximum rates and everything else should all line up. I did nothing to really perturb how the reaction started. It's really only here at the end where it's going to start starving the system out as you start losing A, right? So if we actually run this one, go back to the time course, run that one, we check our graphs. On the concentration versus time graph, look at what happened here to the tail. Instead of having this normal sort of like it goes on forever, well, now you've got something that's actually a lot more sharp. It almost like it ran into the ground. It did not know that it was about to run out of a component. It was running at a rate where as it's running through, it's like, how fast can I run? Look at the species that's running the reaction. Okay, that's how fast I'm going to move. You changed A. It is zero order in A. The reaction is still going to stop dead in its tracks, but what now has happened is the terminal kinetics looks like it was running and it went off a cliff. So this is actually a terminology. If I change my component of what my rate determining component is, and I see this kind of terminal kinetics behavior, it's running into the cliff at almost full speed. The species you changed that became rate determining, or rate limiting, excuse me, the species that became the limiting reagent. I made A the limiting reagent. That is not it has no order in A. It is not the thing that's actually driving the rate in this system. That's also seen here. So this is exactly what you just mentioned. I started fast. It's a straight line, but now I start seeing this curvature at the end right here. This kind of, I'm going. It's running at a rate that's pretty fast, and then suddenly it's like, crap, I'm now super limiting at A. A shouldn't have mattered, but the reaction is going to start to have this massive curvature here at the end. So that die-off behavior is typical of a system that you've made the component, in this case the A component. It's a limiting reagent to allow the progress to happen, but it's not the key thing that's actually driving the rate in the system. You can actually make this way more exacerbated. If I go back to my curve here, and I make this much bigger, so I'm now going to drop it even more. Actually, I have twice the concentration of B. That's the real thing that has the order in the system. A should be zero order. If I run that time course now, you get curves that start to look like this, where it's running super fast, going, and then it just hits the wall. It goes into the ground at full speed, basically. What's happening is, again, think about it. It's charging along. It's looking at the concentration of B for how fast am I allowed to run. It doesn't even care that it doesn't have an eye on the concentration of A. That's not the thing that's actually has a major order in the system. And before it knows it, it's watching B like, yeah, run faster. Oh crap, what the heck? Where's my A? It's just sort of sitting there doing this, looking this way and waiting for A to sort of show up on this side. I used to work construction. My job was to catch paver stones as they were thrown to me and then place them down on the ground. And what happens here is if you're like this to do the catch, one of them's going to nail you in the back of the head, is basically the visual on this. The system had no idea it was about to run out of something because it doesn't have an order dependence in this species. So this is another way that if you have something where those initial kinetics won't allow you to separate what's driving the system, you can follow the terminal kinetics, because that's a hallmark of a system that has a very fast initial reaction followed by a rate determining system. By playing with which one of those components is rate determined, or limiting in the system, stoichiometry limiting in the system, you can see these kind of terminal kinetic behaviors to help you to separate those components. So this is just one way that you can use that sort of terminal kinetics behavior, and I just copied these pieces in. So this would be the concentration versus time profile for something that becomes, I've now made A, the limiting step, and then I make it way more limiting, and what's really we're focusing here is this behavior. If you actually take these curves though, one thing that's really interesting, if you take all three of these curves, this one versus this one, and then the third one, if you were to plot them all on top of each other, what do you think you'd see in terms of the product curve? Like if I took just this curve here from the 0.05a, 0.8a, and 1.5a, and I put them on top of each other, what do you think you would see? So concentration product versus time. Yeah?
The initial curves should all line up until like that choking point.
Exactly. What you'll see is something that kind of looks like that, where there's only these very small differences right up to the point where you ran out of the component. But they basically all what we would call, this is what we refer to as overlay. The curves are basically walking the same step. The chemistry did not care about the thing you changed. The initial concentration of A had no bearing about how you reached that point. But the terminal kinetics, right at that point where you're starting to run out of that material, that's where it suddenly starts to reveal itself. But this concept of overlay is really, really, really important for what we call visual kinetic analysis. This is where you can start using these patterns as ways of digging into systems. I'm going to pause on this one now. I want to go into detail on this one a bit later. It's a way of using the concentration of catalyst versus rate as differentiating between multiple mechanisms. But I want to actually come back to this one to focus on the VTNA arguments. So we mentioned before, initial rates are challenging. They're not something you should be using all the time. They're only really appropriate if you have well-behaved initial systems. There's three things why this gets difficult. And again, this is sort of the doctrination that I was brought into when we started with the Blackman group. And the three things that why initial rates are difficult, just from a data perspective, in order to get initial rate, you probably have to run the chemistry anyway. And you have to set up the reaction and run the whole part, which means you have to do a lot of aliquoting. You're going to do a lot of work to create each one of these points. If you take an initial rate, really what you're doing is taking 15 hours of chemistry, a whole bunch of sampling, huge amounts of data processing, taking 3 or 4 data points and throwing the rest away. That's a crime, right? Like you can use the rest of the entire curve. What I'm saying is you've already gone as far as to run the chemistry, so instead of just using this linear extrapolation to get these kinds of points, you're actually oversimplifying the data, and there's features like what I just showed you in the terminal kinetics that can be just as useful for you to pull out. So in less experiments, you can learn more. The other thing too, and this is a case where if I was specifically trying to extract the order in the catalyst, so in this case, order in the catalyst of the system compared to the rate, the initial rate, linearization is a really, really difficult thing for us to work with because it can very easily hide a lot of other information. It can actually, you've got these gaps in sort of your interpretation, it becomes an overfitting problem. So if I took this is actually an exercise that Jordy did at one point. If you take these data series here and you draw a straight line through it, would everybody feel happy about that? It looks like a straight line, right? If you give this to Excel in terms of a linear sort of fit, you'll get a very high fit. If you were to actually look at the real curve that's actually happening under this point, if I actually trade this here, everybody would agree that the red curve I have against this, not a good fit, right? This is not how I would actually determine what's happening here with the rate of the system versus the initial concentration of catalyst. The reason why is that in order to actually do most of these plots, the concentration and rate, what you're probably going to be doing is something on a power law sort of series. You're going to take your actual data, and then typically what you would do to extract it, to actually fit what the true order it is, you're actually dealing with a log-log plot. That's the kind of typical class of people that will do, is that based on the concentration ranges you're dealing with, you're going to go through and actually carry out some system like this to create a linear feature. The problem with that is that on these two scales, What I'm showing here is the error in those data points on these two different axes. So what I'm saying is if you had a systematic error around those black dots here, what I mean is a systematic error in the rate measurement and potentially a systematic error in the concentration of catalyst. And you imagine that systematic error means that for every data point, just based on the equipment that you have, it will be constant in both axes. So that way we can create a band that falls about that center point, right? Within this point here, both the red curve and black curve are reasonable, right? Within that sort of error range and stuff, both of this sort of nonlinear and the linear fitting are not bad sort of fits. If I were to look at this plot over here, what's happening when you move over to a log-log plot, each of those data points, the error that you put in, has been through a mathematical function which expands across into that data sequence. So this is the same thing for anybody who's done like Lineweaver-Burke plots. You know what I'm talking about? Or what about, not Arrhenius, Eyring plots? If you take a function where you've measured a couple data points, and then what you now have to do is actually plot it on a curve. In this case, if I measure the data point and I plot it on a transformed axis where I'm doing a mathematical function like 1 over x or log of x, your error as you do that is going to expand or contract in a nonlinear way. What I'm trying to highlight is that even if I had a systematic error that was constant around each one of these data points, the error in this one here on this axis is far worse than over here. So if I'm really pushing it to try and get this red curve to bend and fit that last data point, because I really think that the r-squared value, if I was putting it here, that r-squared value is actually lower by choosing that last data point and drawing that red curve. Basically, it's just a reminder that when you've done your experimental measurement, the mathematical transformations you do are important for your error propagation. Remember, as you do multiplications and divisions, the systematic error that you start off with in the normal sort of space will expand in a nonlinear way. So the weights on those errors are different. This is a case where, again, if I was fitting this to a model, I should put lower weight to this one data point than the rest of them in order to get a true sort of representation through that system. The other part, too, is that when you go to r-squared, just as a simple r-squared point, left and right, which of these two feels right or wrong? Well, again, give me your opinion. Why would you think that the right thing to do is draw the blue line through the graph on the left?
I feel like that one's wrong, but that one is okay.
Again, why? What does it?
You can kind of see that there's a bit. It also depends on like the error bars, but you can see a trend of those data points like kind of being systematically below the line and then above the line and then below the line, versus that one is a lot more of a random spread.
And this is where it's a reminder that you don't want to. This is an extreme case, but it happens, right? Where you can look at the graph on the left and say, I think I already see a pattern. The straight line doesn't seem to make sense. Versus, okay, this is a scatter and I'm kind of going through the middle. R-squared on the right looks lower, but it's probably a better fit than on the left. And again, better, what I mean by that is just, is it representing the trend? Are you extrapolating data to get an answer, right? Like, I would say that in the absence of other information, the graph on the right at least says that I don't maybe have full control over my system. My precision may be kind of low, but I could at least go to that system and say, I think I have a linear correlation. If I was going to be planning a new experiment, this line, whatever my responding variable is here, I could vary this down here and actually plan for an experiment with some degree of certainty that it will probably line in this kind of band or range, right? The predictive value of something like this might be better. The problem with something like this is if you're drawing that straight line, you are making a statement about what's happening in the system. You're saying that if I'm drawing a straight line through this, and let's say this was a behavior, I'm neglecting that in those early data points. I'm saying that how the true system behaves is according to that blue line. If how you're differentiating the system comes down to those early points, activation or something else, you've just blown away the important part of the curve in favor of what the average is doing, right? This is the same thing as like, well, everybody else is buying Labubus this year, so clearly that's a good idea. Well, no, mass kinetics doesn't always make the right sort of choices. What I like about this kind of point too, so everybody's used Excel somewhere, right? if you're ever stuck in a place of doing like, how is the appropriate way to treat my data? Something you should feel empowered to do is to take Excel. You can actually create a data series in Excel and then play with it to saying, what if the error on every data point was very large or very small? You can easily create a column in Excel that says, here's my true data, and here's my assumed data, here's my assumed error. You can create a new synthetic data series with those two possible realities. You can carry it through your entire data workflow and then say, what would the consequence of assuming error doesn't matter or it does matter looks like, right? This is something that I have a couple exercises for you guys to try out on this point, but it's basically back to something like this. If you were trying to evaluate and say, is the red line or the blue line in the rate versus concentration space on the left, which one is correct, you could actually add error to each of those data points and create a scatter field in Excel to visualize the whole sort of expanding triangle over here. You can see the consequences of your assumptions as you do this, your data treatment live, and then make a decision whether or not you're comfortable with that. So it's just a simple way, just like the modeling data we have. It's something that you guys can think about by saying, when you're stuck with what do I do, what's the right answer, you can run a series of kind of hypothesis type experiments on Excel to see how does your data treatment actually shade out. So the last one I want to focus on today is this concept of what's called visual analysis. This is a way of replacing both modeling and initial measurements to kind of give you fingerprint kind of analysis to kinetic systems. There's basically two families. There's what's called RPKA, reaction progress kinetic analysis, and then there's this one, VTNA, variable time normalization analysis. The main difference between the two of them, RPKA typically uses a rate versus concentration plot. VTNA uses concentration versus time, or concentration versus what we call a modified time axis. Just in terms for the background literature, there's kind of the 6 main papers that sort of talk through where this history came from and how they get applied. The advantage of something like the RPK method, it's actually way better in terms of data manipulation. Visualizing it is a much truer sort of form of the system. The downside is we don't often have methods to measure rate directly. Usually we measure a change in concentration. Deconcentration dt is what we actually plot as our rate. And if you have, this is an error expanding function. If you take your first 2 data points, your change in concentration, you're doing error associated with that difference divided by error associated with the differences in your time. That division causes the error to expand badly, right? So it's a way, if you have noisy data, trying to use that as a manipulation to get to your rate is troublesome. So this is why, unfortunately, the RPKA data is really only useful if you have a direct measurement of rate, which usually comes down to calorimetry, heat flow in a system. So the math works out way better, but practically it's a bit challenging. VTNA is a little better in the sense that you're using measured concentration and measured time. Both of these two techniques, though, as a warning, right, they're ways of sort of barcoding a reaction quickly. They're good sort of introductions to the system, but once again, you should use them carefully. You can overinterpret them quickly. So how RPK works. You start with usually fractional conversion. We get to concentration versus time. This is usually what we calculate, because what we're usually doing is I'm measuring the heat flow of the system against time, and I know what my initial concentration is. I usually am using math to figure out what my actual concentration curves are, because I'm not measuring that directly. I'm measuring how fast the reaction is turning over by how much heat is coming out of the system. What you can get from that very quickly, though, is if you're doing this kind of fractional conversion or concentration versus time, you get this relative rate versus concentration. That's the plots that I've shown you up here. And what you can, if you can get to those plots experimentally, a normal first order thing looks like this nice descending line where the slope of that line is your K, just like we talked about at the beginning. In cases like this, where you have deviation from that linearity, this is where you have either one or more things with also higher order. So a guy like the graph on the extreme right, that's a case that probably has order in both components of the system. There's more than one thing that's driving the bus, so it's higher than first order behavior. So this is a very quick way to sort of do a litmus test across any other system to look for catalyst deactivations. In order for this to work, it has to be a relatively clean system. What we have to assume when we start to do comparisons between multiple reactions, so for example, if I'm doing this Diels-Alder reaction, I am taking the concentration of A, the concentration of B, these two components, I'm running the chemistry, and I'm making product. The entire graphs we get here only happen because I measured my initial concentration of my two species. I'm not measuring the concentration of my product. I'm assuming a single reaction is happening the entire way through, which means I'm assuming that only 1 and 2 react with each other to make 3. There's no byproducts. 1 does not decompose into something else. 2 does not decompose to something else. 3 does not react with 2. Any of those other convolutions really breaks the math of the system. So one of the criteria for the RPKA method to work is you have to define what they call the excess. The excess is just the difference in concentration between your two individual starting materials. So the excess value is, I would start with some concentration of this, some concentration of this, the difference between the two, whatever it is, I'm assuming that value is known at the beginning and it's constant through the entire course of the reaction. I'm just saying that the mass balance of the system has to be maintained very well for any of these manipulations to work. So it can be large, it can be small, it can be negative, but just in general, the whole point is it must be constant, otherwise the math kind of breaks down. The good news is a lot of systems follow with this, so it's a decent assumption, but it is something to watch out. If you have a case where you're seeing a large distribution of byproducts or selectivity changes, then the interpretation isn't correct. So in this case, if I have these two components, I apply what's called a different excess experiment. That's the language that they use on it. And really all we're saying is I run two experiments where I change the initial concentration of one or the other component. So if I increase the concentration of component 1, my diene, or I decrease the concentration of component 2, I have changed the excess in the system because I've changed the difference in concentration between two components. What you're actually graphing over here is this is your rate of your system against the concentration of one of your components, and we get these kind of curvature and shape. As I work through this, I can actually take that initial curvature, and even though I'm graphing this as the concentration of a single component, what you can do is if I've gone through this case where I've actually varied both of these two components, this graph right here, this is a rate times the concentration times the two different things that are driving this reaction. If I take this arrangement, and let's say take this concentration and divide both sides of the equation there, what I get over there is rate divided by concentration of 2, and on the other side it's just K times 1. The reason I do this manipulation is now this is the same thing that we've done with things like the Lineweaver-Burke or other treatments where we're trying to linearize a plot. By taking the rate measured at any time point at any individual concentration of these components, if I can get a data point like that, by doing this, I'm now graphing, this is my y, so rate divided by that concentration. My x is the concentration of 1. By setting it up like that, the slope of that straight line must be my k value. But again, in order to do this, you have to measure the rate at every time point. You need to know the rate of the reaction at a known concentration of 1 and 2. And as 1 and 2 are being consumed, the rate has to drop accordingly. But it's just a graphical manipulation where if I had a curve that has or have a graph that has this kind of curvature, well, that curvature is because it has order in both of the two components. By taking that instantaneous concentration, dividing the corresponding rate at that instant concentration, I can now create a graph that has this linearity. And it's this kind of overlay perspective is what gives us this kind of part. If you go through the math and derivations that Donna has in those papers, she shows you how to set up the Excel sheets to do this and has practice to allow you to try doing these manipulations. The problem with RPK, like I said, number one is you need rates, which are hard to get. And it's also, again, even though it's simpler than potentially some of the differential math that you have to do, it's still a little bit outside of what we would normally run as organic chemists. We are normally used to seeing concentration of product versus time. So this is where the VTNA method is probably a little bit more palatable. What we're doing here in a similar concept is I would run a series of reactions, and again, I'm now running 2 different chemistries, and what I'm going to do is I'm going to plot the concentration of the formation of product over time for 2 different experiments where the only thing I changed between these 2 experiments is the initial concentration of A. And remember, as you change the initial concentration of A, I'm changing the concentration of A all the way through that experiment. I know that if I start with less A at every time point that I'm showing over here on this side, I will have a correspondingly decreased amount of that component as well. So what that means is I can actually use that change in concentration of A as a way of normalizing the axis. This is the equation that we use to do that. Let me just show you graphically how this kind of works out, because the nice thing is you don't need to do any of the math. There's an Excel sheet that we've produced from this one that just allows you to take your data and set up each of these graphs so you have for visualization. So all of the kind of the dx dt and the d concentration dt math is baked into the Excel sheet. So what I want to focus on is how do you use that sheet and how do you actually apply through the data series. So let's say I had a reaction that looks like this. This is kind of the abridged Michaelis-Menten system where I have only two components. Everything is kind of in this second step here is product and second step, only two intermediates in the system. I would do an experiment that is made up of these 4 experiments. So I'm saying that in order to fully understand or barcode the system, I will run these 4 experiments as a standard. Now, if you look at them, blue versus yellow, what are you changing as you move through that system? So that comparison, the binary comparison of blue versus yellow, would be used to determine the order in A. Okay, what other ones would you do? What color versus what color will tell you what, if you look through these pieces?
Blue and green.
Blue and green tells you
B.
order B, right? What is, let's say, yellow versus red? What's that telling you? Order catalyst.
And the concentration of A change.
And what, sorry?
The concentration of A0 also change.
In yellow versus red.
Right.
Yes. So, well, I think that what the important part of a matrix like this, you could focus on blue versus red is a nice, clean, crisp order and catalyst. Once you know what that is, and if you know blue versus yellow, order and A, you know what that should be. If I know blue versus red, order and catalyst, I would then error check and say, well, based on what blue versus yellow told me, what blue versus red told me, I will follow up with, is it also true that yellow versus red should be the combined order of those two pieces? That's why this is valuable, is it's a matrix of different systems where a series of binary comparisons can not only tell you one value, but it tells you an error check against something else as well. So even though we don't want to be biologists and change a whole bunch of things at the same time, you can do A versus B, like blue versus yellow, yellow versus green, green versus blue. Each binary comparison has a couple of things you could basically focus on. But I agree with you. It's easier to start off and do just the tangible single variable manipulation. Why that this matters is because, I don't know about you guys, if you've ever set up experiments, how often do you hit 1.0? Be honest. Don't basically, when you set up an experiment, you don't sit there and say, I set up a 1.0 molar experiment. No, you probably set it up at 0.95 or 0.98. So once this is up and running and you actually have the full template, you can actually compensate for multiple concentration changes, even if it wasn't the one that you were aiming for. You may have, like, this is the ideal, but there's a possibility when you go to run it that your initial concentration of B was actually different when it was supposed to be your controlled one. And this method allows you to still sort of compensate for those variations. So it's experimentally quite useful. In the end, and again, I'm not going to focus on how we get to the math, but how this works is, if I am measuring the concentration of product against time, that's all this is this is time on this axis. What I'm going to do, now think about it this way. Catalyst is a lot easier to think about. If I have a reaction that, let's say, looks like this. I start the chemistry, product over time looks like that. Great, it's first order in something, it's not just linear. If I increase the concentration of catalyst, and let's say it's first order in catalyst, where would my next curve going to be? Is it going to finish at the same time, finish earlier, finish later? If the only thing I did was increase catalyst, what do I expect to happen? Finish early. It'll run faster, right? And it'll probably run the same movie, just quicker. So I'll just say it's going to look like that, right? The overall shape will be about the same. If I am now going to try and get these two to overlay with each other, the concentration range of product that I have enjoyed is going to be the same. I reached the same level of conversion in both those cases. That's already overlapping. The problem I have to do is I need to squash or stretch my x-axis. I need to find a way that says that on every point, I need to expand or contract these two axes so that they're actually comparable to each other. And if all I did was change catalyst, that's a constant value to every point. I take my time and I multiply it by the concentration of catalyst. That perturbation, that time point times catalyst, what it means is a higher concentration of catalyst, I'll stretch the axis a little bit, and a lower concentration of catalyst, I stretch it less. It allows these two data points to actually start to overlap with each other. I'm normalizing for the amount of catalyst in the system by doing that, right? So that's in your guts, what you're doing with the VTA analysis. I'm not touching my concentration axis. I'm compressing or expanding my time axis, where I'm trying to basically, if something is helping the reaction, I want to compress or expand it more. If something is hurting the reaction, I want to expand it less. And by playing with that value, you can tune this through and solve for the order in that component. The reason it gets a little bit more complicated, when I'm trying to do A, remember, every time point, the concentration of A is changing. So instead of initially, I've got a high concentration of A. Later on, I have a lower concentration of A. So it's not a linear expansion compression like you do with just the concentration of catalyst. Now what you have is sort of this nonlinear expansion where at the beginning, you're actually stretching or compressing more as your concentration A looks different. Late in the reaction has less of an impact and effect. I will post up the Excel sheet to do this kind of point. So on Friday, I'm going to work through this, guys, as a tutorial of here's some data sets, here's how you use that data set, and here's how you apply it. This is really valuable because almost anybody who's doing that point can start to apply these sheets. But I'm not going to dive into how the math actually works after. Okay, guys, I will see you Friday.